All right, so again, today's topic is getting into the area of transformations. And in particular, I know I said this at the end of the last lesson, but I'll describe it once more. We've gone through about a dozen different distributions at this point, discrete and continuous. And so what we're about to get into is, what if you have a scenario where you have a new random variable that's a function of a random variable that whose distribution you know. And you'll see as we get into problems, hopefully that description will make more sense. But if you know that, for example, X is gamma distributed, and you want to find Y, how is Y distributed when Y is e to the X power, then you're going to learn how to figure out the distribution of Y in that case. And I believe that is the first example here that I just described. So let's just jump right into how you'd actually do this. This handout is starting from first principles. So the next one's going to get into a shortcut, but it's important to understand how what I'm about to show you works. And personally, I like starting from first principles because it always holds true. And so the way that this works, and the reason why this is called the CDF approach, is because first you want to find the CDF of the distribution that you're looking for. Your ultimate goal is a PDF. So if you end up getting the CDF, how do you get a PDF from a CDF? Anyone remember? Do you remember the relationship between a probability distribution function and a cumulative distribution function?
You take the derivative.
Mm-hmm. Yeah, thank you.
I just read the thing.
That's fine. If you need to look back, now is the time to do so. Yeah, so in the continuous sense, I'll just make a note over here that remember that f of x is the PDF, and that capital F of x is the integral from whatever the lower bound of the support is up to, I'll say, x of little f of t. And so if you have a CDF, then to go from a capital to a lowercase, you need to take the derivative. And so that's what we're going to do. And sometimes we'll use a trick. Sometimes we'll actually take the derivative directly, and you'll see both of those cases. For this first one, we want the distribution of y. Y is equal to e to the x power. X has a known distribution, the gamma distribution, with parameters alpha and theta. And so first we want to figure out, well, what is the CDF? So first principle says that f of y, because this we want the CDF of y, is the probability that capital Y is less than or equal to little y. And I'm going to put a subscript on the P just to indicate the distribution that comes from. So here, to find this probability, we would use the distribution of y, whose distribution we don't know yet. All right, that's the whole goal of this problem, is to figure out, well, how is y distributed? But we do know that capital Y is e to the x. So I make that substitution in for capital Y. And now I'm going to manipulate the inside so I have x, not e to the x, which means I need to take the natural log of both sides. So that's going to give me the probability of x is less than or equal to the natural log of y. But now the random variable in this statement is x. So the subscript on P is the distribution of x, whose distribution we do know. Now I didn't change the subscript here because even though there's an x inside the P notation, it's not x, it's e to the x, and e to the x is y. So we didn't get x alone yet. That's why the subscript on P is still y, not x. All right, so from here, now we're actually going to solve this probability. We're using the gamma distribution because that's the distribution of x, where gamma has support 0 to infinity. So we're going 0 up to the upper bound in our P statement. We want the probability that x is less than or equal to the natural log of y. And the gamma distribution, if you have it memorized, great. If you don't, you could always look it up. And that's your gamma distribution, the PDF. I'm going to come back to the screen, but again, remember I have this table posted on Lilima. So if you forgot that, or haven't looked at it, or haven't printed it up yet, it's at this point where it may be really helpful for you to just recall it as a resource. And so the gamma distribution is the third one here on the continuous side, and the PDF is that third column. And so that's where the gamma alpha theta PDF is, or came from. All right, so this is the point we're at. Now this is, for all intents and purposes, it looks like an impossible integral to actually solve, because even though integration by parts seems like the right option, we don't have a value for alpha. If alpha were 1, then the x term would disappear. If alpha were 2, you do integration by parts once. If it were 3, you do it twice, but we don't know what alpha is. And so I'm going to use a trick. And the trick is this. I don't actually need the integral. What I want is little f of y. And Miku, was it you that spoke up before? Did you say take the derivative? Whose voice is that?
Mm-hmm.
Yes, see, I'm starting to recognize voices. All right, so Miku said, well, if you want little f of y, take the derivative of the CDF, capital F of y, which means I want the derivative of the integral of the PDF. And back in Calc 1 or 2, I'm not sure where it would have come up for you guys. You should have learned a trick to when you take the derivative of an integral. Does anyone remember what you do? I'll give you a hint. It's a fundamental theorem of calculus. Is it ringing any bells? It cancels. So that's part of it, Tony. It does cancel. I see I've got 2 chat messages. Alvin, it's going to be transformations. It'll definitely be this one, which is by CDF, and then the other topic that will be covered is the shortcut. I'm not sure if we'll get to the third one. Yes, so evaluate the integrals, sort of. So what ends up happening is the integral does disappear, and you end up taking the variable piece and plugging that in for x. And so that log y, every x becomes log y. So that's usually the first step that I do. We've got 1 over the gamma function of alpha, theta to the alpha power. Then x is the natural log of y to the alpha minus 1 power, e to the negative, and x again is natural log of y over theta. But then the other step is to take the derivative of that bound. So the derivative of the natural log of y is 1 over y. And so I'm not quite sure, Tim, if that's what you meant by evaluate the integral, but I will give you the benefit of the doubt. Take the credit even if it's wrong. And so over here, this is the answer. You could simplify it a little bit. For example, this or the power of the exponential negative 1 over theta times the natural log of y. You could use log rules, and you could do manipulation like this. So negative the natural log of y over theta is negative 1 over theta times the natural log of y, which is the natural log of y to the negative 1 over theta. And that's helpful because in the end, we want e to that, e to this, e to this. And what do you know about the exponential of a log? It becomes the exponent. Yeah, good, Alvin. And so this is just y to the negative 1 over theta. So that's neat because this 1 over y is y to negative 1, which means that we can combine a couple of terms to simplify this a little bit, and we could rewrite this PDF as this. All right, so the constants are the same, 1 over gamma of alpha, theta to the alpha. The natural log of y to the alpha minus 1 didn't change. But what I did was I realized I had a y to the negative 1, and that the exponential term is y to the negative 1 over theta. And so if I combine by multiplying by y to the negative 1, you get y to the negative 1 minus 1 over theta, which is y to the negative 1 plus 1 over theta. And when you have something to a negative power, that's the same as 1 over that something to a positive power, which is why I don't have any negative signs in the denominator in my answer. You can get a common denominator for the power of y. It's not really a required step, but it's fine to do that. The last thing that I'd be looking for is to determine the support of this distribution. And the way that you do that is typically going back to the relationship that was given at the beginning, which is y equals e to the x. Now, x is gamma distributed. What is the support of the gamma distribution? Anyone? What can x be if it's gamma distributed?
0 to infinity.
Thank you. Yep, 0 to infinity is what this table says. So keep that in mind. So x goes from 0 to infinity. At its smallest, what will y be?
1.
And that's when x is 0, so e to the 0 is 1. And at its largest?
0.
So as x goes to infinity, what is e to the infinity?
Infinity.
Yep, so the support here is y goes from 1 to infinity. And this happens to be known as the log gamma distribution. That's not something you had to know. I would never expect you to actually know that this is the log gamma distribution, but you just derived one that you didn't know. So that's where the log gamma distribution comes from. It is related to the gamma distribution. Even though it's called log gamma, it is not the log of the gamma. Notice that it's the exponential of the gamma distribution. So let's take a look at problem 2, just so you get more examples under your belt. W here has a uniform distribution from negative pi over 2 to pi over 2. And we define x as tangent of W. We want to know what is the PDF of x. So using CDF approach, this means I want capital F of x, which by definition of CDF is the probability that x is less than or equal to little x. So this is under the distribution of x. We know that x is tangent of W. So I'm going to make that substitution now. Which means now when I solve for W alone, what do I have on the right side? How do you get W alone inside the parentheses?
Inverse tangent.
The arctan of x. And now W is alone, so this probability is going to be using the distribution of W, which we know. We know that W has a uniform distribution. So at this point, we are going to be integrating over the PDF of W. What is the PDF of W? How do you get the PDF of a uniform?
1 minus b, 1 over b minus a.
And B here is?
Pi over 2.
And A?
Negative pi over 2.
All right, and so what is 1/2 minus a negative half?
1.
And so I had pulled that pi out. So this is really just going to be the integral of 1 over pi dw. What are the bounds for the integral? What's the lower bound? Remember, we're integrating with respect to W, and you know the support of W is inherently given in its distribution?
Is it negative pi over 2 to pi over 2?
That's the support. And so which one of those is the lower bound?
Negative pi over 2?
Mm-hmm. And what do we want to integrate up to?
Pi over 2?
But what does the P statement say? We want the probability that W is...
Less than or equal to.
Wait,
I'm not sure.
The arctan, that's our upper bound. Now you can use the first fundamental theorem of calculus like we did in the first problem, but in this case, yeah, the integral is really easy. So we could just integrate this to get 1 over pi W evaluated from negative pi over 2 up to the arctan of x, which is arctan of x minus a negative pi over 2, which becomes positive, over pi. And this is the CDF. So now that we have the CDF, Miku, remind me again, how do you get the PDF?
Take the derivative.
Thank you. So we take the derivative with respect to x of capital F of x, which we just found. What is the derivative of arctan? Or does anyone remember what you can take the integral of to get arctan? So the derivative of arctan is 1 over 1 plus x squared. It's just one of those fundamental integrals or derivatives that you would just have to know. The 1 over pi comes from the denominator in the capital F of x. And the pi over 2 over pi, or 1/2, is a constant. So when you take the derivative of the right part, the second entity, that's just 0. And so this is our answer. And if you evaluate the support, the tangent of negative pi over 2 and the tangent of pi over 2 are both plus and minus infinity. And so x goes from plus to minus infinity. It's the full real line. This one happens to be a known distribution also. This is called the Cauchy distribution. So there are a few more problems on this handout, but at this point, having gone through 2, any questions? Tony, I see earlier, I may have missed it when you actually wrote it, but do you understand why for the first problem, the support is 1 to infinity and not 0 to infinity? So do you do you know that the gamma distribution has support 0 to infinity? Okay, and so remember that x is gamma. So we know x goes from 0 up to infinity. Now y is e to the x. And so at its lowest bound, when x is 0, what's e to the 0? And then as x gets bigger and bigger and goes to infinity, what's happening to the exponential function? Yeah, it goes to infinity. And so that's why the support is 1 to infinity for y. Let's see, Alvin. What was your -1 to 1 question mark answering? I'm not quite sure. Bounds for 2. So the bounds for integration come from the fact that we are integrating with respect to W's distribution. And W we are given has the uniform distribution. And remember that the uniform spans from A to B. So based on what is given in its problem, it starts at -π/2 and goes up to π/2. Is that clearer, or you're still unsure? Okay, great. I don't think I missed anyone else's comment or questions, but are there any lingering ones? Okay, so let's take a look at the third one then. In this case, you are essentially told the distribution that you want to derive, or at least you're told the name. And so here we say that we want to prove that y, the random variable y, has a uniform 0 to 1 distribution if x has the logistic distribution, and here the PDF for the logistic distribution is given. We have the relationship of y with respect to x as y equals 1 over 1 plus e to the negative x. And so we just want to prove that when x has the logistic distribution, y will have a uniform 0 to 1 distribution. So that's our goal. All right, so again, start off with first principles. Ultimately, we want to derive the distribution of y, which means we want capital F of y. And based on just the definition, this is the probability that capital Y is less than or equal to little y. And we can substitute in what y is here, which is 1 over 1 plus e to the negative x. And then what's left is to solve for x alone. So you have to be careful with your manipulations. So let's take it a step at a time. I'm going to multiply the denominator through. So this gives us the probability of 1 less than or equal to y times 1 plus e to the negative x. Then let me multiply through by y. That'll give me y plus y e to the negative x. So I'm going to bring the y to the left, and I'm going to flip because I want my random variable on the left side. It's just poor grammar to have it on the right. So this is the probability. I've got y e to the negative x. Now, if you think about it, the greater than part is next to the y e to the negative x. So when I have it on the left side, this is the sign I should have with it. And on the right, I have a y minus 1 when I subtract the 1 from the left to the right. Then I'm going to divide by y. And then take the natural log of both sides. And then finally, multiply both sides by -1 to get a x instead of negative x. When you multiply by a negative sign, you also have to flip the inequality. And if you ever have trouble remembering that, just put, some fake numbers in. So we had, let's say, 3 is greater than 2. And if you multiply by -1, should it still be a greater than? All right, Alvin, I see your question. Let me tackle that in just a moment. No one answered mine, so hopefully you realize that -3 is not greater than -2 and that this should be less than. And so it's, if you just throw some true numbers for the first scenario, multiply by -1, see what happens just to make sure that you have the right symbol. So Alvin says, shouldn't we have essentially 1 minus y? So let me check my algebra. And it does look like it should be, yeah, so we had a 1 minus y, and that's what you were referring to, Alvin, right? In my second line there. And so this in the end should be negative log, it should be switched. All right, so this should be 1 minus y. And then we would have a 1 over y minus 1 here, which would give us the natural log of 1 over y minus 1 over here, and then negative the natural log of 1 over y minus 1 here. Thank you, Alvin. And so it's at this point that we're going to do the same idea that we did in the first problem. So I'm going to set up the integral, which is using the distribution of x So this is going from the lower bound of negative infinity up to negative the natural log of 1 over y minus 1. And we are integrating the logistic distribution of e to the negative x over 1 plus e to the negative x squared. And we're going to apply the first fundamental theorem of calculus. So we're going to take the derivative of both parts. So little f of y is going to be e to the, I'm going to bring that negative sign in, and I'm going to manipulate what's inside. So what I mean by that is this 1 over y minus 1 is the same as 1 minus y over y. And when you write negative the natural log of 1 minus y over y, this is equal to the natural log of the inside to the negative 1 power, which is the same as the reciprocal. So I'm going to write it like that because it gets to simplifying a little bit faster. And then on the bottom, we have 1 plus e. Wait, hold on. Nope, that negative sign's actually going to cancel out. Yeah, I apologize. Let's keep it as this form here. And that's because you have e to the negative x. So when we substitute this in, the negative signs cancel, and you just get e to that natural log. So that is one minus y over y. And so we could simplify these exponential terms. On top, we have 1 minus y over y. On bottom, we have 1 plus 1 minus y over y, and that quantity is squared. And that 1 minus y over y, remember, is 1 over y minus 1, so the 1's are going to cancel out on bottom. So we've got 1 minus y over y on top, 1 plus 1 over y minus 1 on bottom. And this is going to give us 1 minus y over y times a 1 over y squared, which when you multiply by the reciprocal is y squared. And we have one of the y's canceling out. And so we get y minus y squared. And what is missing is we didn't apply the first fundamental theorem of calculus completely yet. So we did substitute in for x, but we didn't multiply by the derivative, remember? And so we also need to multiply by the derivative of the negative natural log of 1 over y minus 1. And so the derivative of this term, so dy of the natural log of y over 1 minus y is going to be 1 over y over 1 minus y times the derivative of the inside. So this is quotient rule. So for me, again, you may have been taught quotient rule a little differently. So I do low d high minus high d low over low squared. And that's how I remember it. If you remember it differently, that's fine. So let's start simplifying. This is 1 minus y over y when I take the reciprocal. The quotient rule portion is 1 minus y plus y over 1 minus y squared. The y's on top cancel out. One of the 1 minus y squares disappears, and this is 1 over y minus y squared. So I need to multiply that part in. Now, it wasn't critical until the end. Because it's here. Where you see what happened. What's our final answer? What do you get when you multiply those two or divide appropriately, whichever way you
Isn't
do
just
it?
1?
You get 1. So we get 1. Now let's figure out what the support is. And so we know x went from negative infinity to positive infinity. When x is at its smallest, e to the negative x, or e to the negative infinity, blows up, which means what's happening in the denominator of how y relates to x is the denominator gets bigger and bigger. So 1 over a huge number is essentially what?
Zero.
0. So we know that the support starts at 0. And now we need to view the other extreme. So as x gets bigger and bigger, e to the negative infinity approaches 0, which means you have 1 over 1 plus 0, or 1. And I don't actually need that equality portion. And so now we have that the distribution of y is 1 with a support 0 to 1. Both of those details together prove that this is a uniform distribution from 0 to 1. So that's our proof. We had to get the PDF and we had to confirm the support. Any new questions pop up?
Can you show the whole problem? Like with all the work? I was kind of a lot, but I didn't copy some part of it.
So our goal was to prove that the distribution of the random variable y has a uniform 0 to 1 distribution. When y is related to x by y equals 1 over 1 plus e to the negative x, and x has what's called the logistic distribution, which is the little f of x function given in this problem. So that's the setting. We know the distribution of X, we know how Y relates to X, and we want to prove that Y has a uniform 0 to 1 distribution. So how we did that was we start off with, well, we want the CDF of Y, which is capital F of Y. By definition, the CDF is the probability of being less than or equal to the lowercase letter, which is how I've started every problem so far. From there, in step 2, I substitute in for the random variable that we don't know, which is capital Y. Then step 3 onward for a while, I ended up manipulating through algebra to solve for X. And so I multiplied both sides by the denominator. I subtracted and divided appropriately in order to eventually solve for X right here. And so now we want the probability with respect to X, which we can find because we know X's distribution. It has a known distribution that was given to us. And so it's at this point that I just follow what we did 2 chapters ago, which is to get a probability, you need the area under that curve in the desired region. So that region for X is from negative infinity up to what the P statement says, which is negative natural log of 1 over Y minus 1. And then what's inside the integral is the PDF, the logistic distribution. I used the first fundamental theorem of calculus, which is the derivative of an integral. Is the integrand evaluated at the random variable, which is the negative natural log of 1 over Y minus 1 term, times the derivative of that, what we plugged in. So the derivative of the negative natural log of 1 over Y minus 1 happens to come out to be 1 over Y minus Y squared, which I had solved in red over here. So that's where that came from. We ended up working through kind of keeping the natural log, keeping the black stuff and simplifying that. It wasn't until the very end that we actually multiplied by the derivative portion. And when we did that over here, it turns out that we get 1. And then our last step was to think about, okay, well, what is the support of this distribution where the PDF is 1? And so we went back to the relationship of Y and X. We know the support of X, so we think about, for all the X values, what can Y be? In this example, you really only have to consider the 2 extremes of X, which is negative infinity up to positive infinity. And it's kind of from a limit perspective. So as X gets really big, the exponential term on bottom goes to 0, and you're left with 1 over 1 plus 0, which is 1. That's our upper bound for Y. And when X gets really, really small, as E goes to negative infinity, you get E to the positive infinity, which explodes. It's a really big number. So you have 1 over a really big number, which is approaching 0. And so that's how we got Y between 0 and 1 for our support. And that's exactly what the uniform 0 to 1 distribution is.
Oh, wait, can you go back to the part where you took the integral, the derivative or something? It was like on the right, kind of not showing. Yeah, that part.
Did you have a question, or you just need to see it again?
I need to see it.
Okay. So while Sydney's looking, if you guys happen to have the documents in front of you yourself, feel free to take a look at the next problem. You're welcome to try to start tackling and setting it up and see how far you can get. And Sydney, let me know when I could move.
Okay.
Okay, I could switch.
Yeah.
All right, so here is the fourth and last problem on this particular method. It says if X has this particular PDF, so this one doesn't have a name, and that's fine. It doesn't have to come from a named known distribution. We want to know what's the distribution of Y when Y equals X squared. And so we want to progress from here. How would you start?
Get the CDF of Y.
Okay, so we want, whoop, I don't need rainbow colors. So we want the CDF of Y, which by definition is what?
Y less than little, or Y less than or equal to little y.
Mm-hmm. And then what would your next step be?
Substitute X squared in for big Y.
All right, so far so good. And then what?
Square root X squared, or both sides.
Both sides. So you would want to square root. And what would you write? Because this is where you may make a mistake on this particular problem.
Would you do negative, or wait, negative root Y less than or equal to X less than or equal to root Y?
Yes. Awesome. Yeah, so that's that's the part in this problem where a student might miss a detail and just write X less than or equal to root Y. Remember, the square root's really plus or minus, so you need both aspects. And so this is the probability that we now want to find. So as we progress from here, now we want the integral of x squared over 3 from negative root y up to root y. And again, you can, excuse me, you can use the first fundamental theorem of calculus, or in this case, it's a pretty simple integral to evaluate. I'd probably just go ahead and evaluate it. So what's the integral of x squared over 3?
X cubed over 9.
Thank you. So it's x cubed over 9, which again, you're evaluating from negative root y up to positive root y. Or you could view that as negative y to the 1/2 up to y to the 1/2. That'll make things easier in the next step. So when you evaluate, you've got y to 3/2 over 9 minus a negative y to 3/2. Sorry, that's secretly a 2 over 9, but the negative signs make this a positive, which gives you 2/9 y to 3/2. And then you refocus and you say, wait a second, this is the CDF. So Alvin, what do we do in order to get the PDF? Yeah, you take the derivative. So we want little f of y, which is 2/9 times the derivative, which is 3/2, bring the power down, rewrite your base, subtract the 1 from the power, and then simplify. You get root y over 3. And then you look back at the support. And so this one is a tricky one because it's not the bounds of x that are really going to give you the range of y. I'll do the easy part. I could tell you that y at its largest is going to be 4. What is its smallest value? Remember, y equals x squared. So when x is 2, y is going to be its biggest, which is 4. What's the smallest y might be?
1.
So one's a common answer that I'd get, because if you square -1, you'll get 1. But it could actually be smaller than that.
0.
How'd you get that?
Because it can be between -1 and 2, so it can also be 0 squared.
Perfect. So this is a case where you do need to think a little bit harder about the support of the variable whose distribution you do know, and think about what might look like. And so in some cases like this one, doing a little sketch might actually be advantageous. And what I mean by that is you could kind of view the support like this. And so this is essentially y equals x squared is the quick sketch. X is on the x-axis, y is on the y-axis. And so even though I could see that x goes from -1 to 2, looking in the y direction, I could see that y is going to go as low as 0 and as high as 4. So if I really want to be picky, I could actually see that this would be y greater than or equal to 0. But it's not actually going to get to 4. It'll get close to it. So I'm not too picky about that aspect when you're writing supports, but web work might be. I'm not too sure.
But why is y greater than or equal to x squared again?
You're talking about this part?
Yeah.
It's because we know that in the previous statement, we have capital Y less than or equal to y, little y. But we're told that capital Y is x squared. So we substituted x squared in for capital Y. That's why x squared is less than or equal to y in the underlined statement.
Wait, is it always it's always capital Y is less than or equal to y, yeah.
Yeah, every time, whatever your random variable is, for the distribution you want to find the distribution of y. The CDF is P of capital Y less than or equal to little y. I thought we had, oh, okay, problem 2 used a different letter. Here we knew the distribution of w, so we wanted to find the distribution of x. So here we had P of capital X is less than or equal to little x, because back in, maybe it was in discrete actually. Wow, was it even earlier? I don't remember where it came up. Let's see. No. Does anyone recall where cumulative oh, here. Okay, the first handout for continuous distributions, the cumulative distribution function, capital F, is P of the random variable less than or equal to the little letter. So that's always, by definition, the cumulative distribution function.
Okay.
All right, so before we move on to the next handout, any questions on any of the problems that we've gone through on this one?
Wait, when are you gonna update the lecture videos and like post this one and stuff?
That's not a question about this, but at least the past two lectures I have, and I'll post them right after this lecture. But any questions
Okay.
on this particular handout or topic? Okay, so again, this is the fundamental approach to deriving distributions of random variables. And this next handout shows you a shortcut for doing it. It's not that drastic of a shortcut. And so personally, I think it's easier to work from what we just did, but you can make the decision when you see the next handout if you feel the same. All right, so the derivation for this shortcut is given in the the top part of this handout. And mainly you'll notice that the pattern is what we've been going through. So the CDF, which I'm calling a capital G of Y here, by definition is the probability that capital Y is less than or equal to little y. Your capital Y is usually some function of x, so I'm using u of x as a general function, which means that x can be written with respect to a function of y. And so I'm using kind of like, it's not an inverse function, but u inverse is v. So I changed a letter, v of y, which means that here, the probability that x is less than or equal to v of y, this is a CDF, but this is the CDF of x. And so now I'm using capital F. I have an x subscript so that you realize that is from the distribution of x. And this CDF is evaluated at v of y. Now, this isn't at the shortcut yet. The shortcut comes into play with the first fundamental theorem of calculus, because what we did in at least two of the problems on the last handout was before we integrated, we just took the derivative directly. So little g of y is the derivative of the capital F function. Now, this is chain rule. This is a function within a function. So when you take the derivative of this, you're going to get capital F prime, which is little f, times the derivative of what's inside, which is your v function. And so in the end, your shortcut is to use this notation, this particular approach. So it's essentially what we've been doing. It's just we've really have been working through every step, whereas now you could really jump straight to it. It does require that your, let's see, the function that your random variable is equal to is monotonic. Does anyone know what monotonic means? It happens to be defined right there.
Doesn't go up or down, or
Mhm.
up and down. I mean,
Yeah, it only goes one way. So either it's always increasing or it's always decreasing. The rate doesn't have to remain the same. So it doesn't have to be linear. An exponential function is monotonic, okay? And so it can't go up and down. But what's really important is that it's monotonic on the interval you're looking at. And so that's the key. That's what you're really focused on. So for example, in this last problem here, clearly from -1 to 2, it is not monotonic according to my graph, because it goes down, then it goes up. But if I had really just been looking at 0 to 2, then it is monotonic. Even though the function y equals x squared isn't, it's monotonic on that interval of interest. And so it's important to keep that aspect in mind. All right, so we're going to go through and we're going to solve these problems using the shortcut. At least the first one is one that we did in the last handout. So you already know what the answer is. You're just going to get a feel for how you could jump straight to the answer a little bit faster than first principles, which we did on the last handout. So let's go ahead and see. By the way, there is a slight difference if your x distribution is discrete, then notice that you don't actually have a derivative part in there. It's just the discrete PMF evaluated at your v of y function. I think there will be an example in here somewhere with that. But let's take a look at number 1, which isn't discrete. So we've
Can you
got,
scroll up? Like, what's the name of this lesson again?
it's called change of variables. It's a shortcut approach to the CDF approach.
Okay.
All right, so we have, just to use notation that you see up above, we've got that u, or u of x, is e to the x. Now, if we take this and we solve for x, we get x equals what?
ln of y.
Yeah, the natural log of y. Now that is our v of y function. Now, according to what this shortcut says, is we want to take the f of x function, evaluate it v of y, and multiply by v prime. So we have u, we found v. What else do we need? We also need f of x, the PDF of x, which we are given to be gamma. So that is 1 over the gamma function of alpha, theta to the alpha power, x to the alpha minus 1, e to the negative x over theta. So then the shortcut says that we take this distribution, but we evaluate at v of y, which is the natural log of y. So x becomes the natural log of y, and multiply by v prime. And it is absolute value. That's what those brackets are, if you forgot. And so if your derivative happens to be negative, make it positive. It's not negative in this case. So v of y is the natural log of y. Derivative of natural log of y is 1 over y. And then from here, this is exactly what we had right at this point. And so you would make those same manipulations if you wanted to simplify a little bit more. And you end up with the same answer. And you should. If you do both of them right, you should end up getting the same answer. So it's a good check so that you could see that the method does actually work. And then of course your support is going from 1 up to infinity from the same reasoning that we did in the last handout. And that's how you apply the shortcut. I don't know if you guys feel like it's a shortcut. It just skips some of the writing, but a lot of the reasoning for it is the same. Let's take a look at problem 2, because this is a new one. This wasn't on the last handout. In problem 2, we want to show that W, which is equal to x minus a over b minus a, is a uniform 0 to 1 distribution if x is uniformly distributed from a to b. So that's what we want to work through. Let's write down some of what we know. So we've got that, let's see, u of x is x minus a over b minus a. If you solve for x, that's going to give you v of w, which will be a plus b minus a times w. So that, if you're not sure where that came from, I took this equation and I solved for x. So x equals, that's your v of w function. And I also know that f of x, since x is uniform a to b, this is 1 over b minus a. Questions on any of the details that I've stated so far for this problem? Because I haven't actually derived anything. I just stated either what was given or it was pretty quick to find. How'd you get VW again? So I got VW by solving for x. You're welcome. Anyone else with a question? All right, so we have almost all the information we need in order to actually apply this shortcut. So let's go ahead and jump to the shortcut. So we want g of w, which is going to be f of x evaluated at v of w, but there's no x to sub in for, so this is just still 1 over b minus a, times the derivative of v of w. and the derivative is b minus a. So we get 1. And then you think about the support and you say, okay, well, x is uniform from a to b. So when it's at its smallest, when x is a, w is 0 because it's a minus a. And when x is b, you have b minus a over b minus a, which gives you 1. And this is a uniform 0 to 1 distribution. So far, so good? It just feels unusually quiet on my end, at least.
So I totally get what we did, but how did we just show that the distribution is uniform 0 to 1?
So what do you know about a uniform 0 to 1 distribution? What is the support?
0 to 1?
Is that a guess? You make it sound like a guess.
Yep.
So here on this table, it has a general uniform A to B. But if A is 0 and B is 1, then according to the fourth column, your variable would go from 0 to 1. So that's one thing.
Mm-hmm.
But then also, if it is uniform 0 to 1, 1 over 1 minus 0 is 1. So your PDF will be 1. And so we
Okay.
that we have both of those aspects, which we do here. So we have that the PDF is 1, and we have that the support is 0 to 1.
Oh, okay, I get it.
That is why both of those together show that this is a uniform 0 to 1 distribution.
Okay, thank you.
You're welcome. Anyone else with a question? All right, I don't see anything on the chat board, so let's take a look at number 3. And this is our first discrete one. So we are given that x is Poisson 4 distributed. We want to find the distribution of y, where y equals the square root of x. Is y equals root x monotonic? Yes, yeah, Miku says yes, which is true. If you're unfamiliar with the square root function, it looks like that. And so it's always increasing, starts at 0 and goes up. And so it is monotonic. I didn't check the others, or at least I didn't discuss them, but in number 1, y equals ECX is exponential, which is always increasing. And then number 2, w equals x minus a over b minus a is a line. So if you divide through, you have a slope of 1 over b minus a and an intercept of negative a over b minus a. So this is a line which is monotonic. And so in both of those previous two problems, we've satisfied monotonicity. So in this one, we have a discrete distribution, which means our shortcut is a little easier than what we've done. There's no derivative to account for. You just need to evaluate at your v of y function. So let's get the information that, that we know. So we've got that u of x is the square root of x. And if you solve for x, you get v of y equals what? if you solve for x here, what does x equal?
Y squared.
Mm-hmm. And we know that our it's little f of x, but I know that just to stick with notation you guys are used to from the discrete chapter, the PMF of Poisson, does anyone happen to have that memorized? Not yet. E to the negative 4 times 4 to the x power over x factorial. So e to the negative lambda times lambda to the x over x factorial, but we're given that lambda is 4 right there. So that's why I plug that in. And so according to the shortcut, the distribution of y is going to be given by taking the distribution of x and substituting in v of y, which means we have e to the negative 4 times 4 to the y squared over y squared factorial. Now x for Poisson can be 0, 1, 2, 3, and so forth. So it's, remember, it's discrete, it's count, integers only. And so y, not equal, sorry. Y could be 0, 1, root 2, root 3, square root of 4 is 2, and so forth. And that's it. So y is it's not quite discrete, you know, they're not all integers, but it is a valid distribution. So even though what y can be seems a little awkward.
Wait, how did you get y? Is it just like, where'd you get the square roots from?
Because y equals the square root of x. And so for all the possible x values, y
Oh,
can
okay, I
be the
got it.
square
Got
root
it.
of them. Sorry?
All right, it makes sense. Yeah.
Yeah, so that's where the 0, 1, root 2, root 3, 2, and so forth came from, was square rooting all the values that x can be.
Wait, why is lambda is 4? I
'Cause
thought,
it's given to us.
huh?
It's given to us.
Oh, is that? I thought that would be like x or something.
No. When you write the Poisson distribution, it's always Poisson of the parameter of the distribution. So in this case, the value listed inside corresponds to the parameter value. Is that what you're asking for, or am I misunderstanding your question?
Why does v of y is like, why do you have to write that's y squared?
Wait, why am I writing y squared?
Oh yeah, because like,
That's your question, right? Why is y squared? What do you get when you solve for x here?
I mean like, yeah, but
So like Sydney, x equals what?
that c of x is x square root of x. Is that like y square root of x?
No, y equals root x. So when you solve for x, x equals what?
Oh, you're solving for x?
Yeah, in all these, we always solved for the other variable. So in number 1, y was given as e to the x. So x equals natural log of y. So we solved for the other variable. In number 2, w equals x minus a over b minus a. So what does x equal? X equals that, your v of w function. And then number 3, y equals root x. So when you want to solve for what x equals, it's your v function. Sydney, does that answer your question, or is there something else?
So x is y squared, so you replace 4 to the x with 4 to the y squared.
Well, you replace x with y squared because right here it says that you're evaluating the f of x function at v. So since v of y is y squared, wherever there's an x, it's a y squared now.
Okay.
All right, so problem 4 doesn't directly look monotonic. Again, this is a case y equals x squared, that's a parabola, but it will be monotonic. Does anyone see why? Remember, my hint is that you really only need monotonicity over the interval or range that you're interested in. What is that range here?
Is it 0 to n?
Mm-hmm. Yeah, it's non-negative values. And so x is binomial. So that means x can be 0, 1, 2, 3, 4, and so forth. So let me write that down. So we know that p of x is n choose x, p to the x power, q to the n minus x power, or you could write 1 minus p if you prefer. And x, again, starts at 0 and goes up to n. So this is your binomial PMF. Now this means that y equals x squared is monotonic over these values because it goes from 0, 1, 4, 9 up to n squared. So it's only increasing, it doesn't come back down. Which means we can use the shortcut. And because x is a discrete distribution, we're using the extra shortcut, the shortcut if you tend to view it that way. So we want the distribution of y. We have that u of x, which is the one given, is x squared. And when you solve for x, you get v of y, which is what? What is x equal to?
Square root y.
Mm-hmm. Yep, square root of y, which means that the distribution of y is the distribution of x evaluated at the square root of y. Would you need to consider plus and minus? No, you wouldn't, because remember that based on the x values, you're never going to have a negative, corresponding negative y value. And so you won't have the negative side. Okay. All right, so I was saying now you take the PMF of the binomial, and wherever there's an x, you're subbing in your root y because that's what x is. So we have n choose root y, p to the root y times q to the n minus root y. And our support is 0, 1, 4, 9. It's all the squares of the x's up to n squared. There is one more problem left. Any questions on any of the ones that we've done so far? We've got plenty of time. All right, I want to give you guys a chance to see if you can, how much progress you can make on doing one of these problems. So take a look at 5. You could try either the shortcut and or the CDF approach. Both would work fine. And see how far you're able to make it. I need some feedback on that end. So I'm going to pause the recording. I'll give you a few minutes to try and make progress on the derivation of the distribution of y for number 5, and then I'll seek your input in a few minutes. Once more. Okay, so we're going to start going through number 5. Tony has unofficially volunteered to provide the u of x and b of y functions. So what did you get for u of x? -2 theta log x. Yeah, so that is what's given. So -2 theta times the natural log of x. And what did you get for v of y then? You got e to the y over 2 theta. That's close. There's an error in what you typed. Does anyone see what's off?
Should be e to the y over -2 theta.
Yeah, the negative sign should be inside the power. So you should have e to the -y over 2 theta. And that should be your v function. Tony, do you see that? All right, good. All right, the other detail that you need, since x is continuous, is you'll need v prime. And Tony, I know you didn't say that you got this, but I have faith in you. Would you mind telling me what the derivative of that v function is? All right, good. Yeah, so you got -1 over 2 theta e to the -y over 2 theta. So that is your derivative. So now we've got all the pieces that we need in order to use this shortcut. So remember that your g of y, which is what we want to find, is going to be f of v of y. F is the PDF of the distribution that we know, times the absolute value of the derivative of the v function. And I emphasize that part because in this case, our derivative is negative. So absolute value is going to be important here. All right, let's see. So we start plugging in. So the f function is the one that's given. So we have theta times x, where x is our v of y. So we have e to the negative y over 2 theta. And that is to the power of theta minus 1 times the absolute value of v prime. And v prime, the absolute value of it is 1 over 2 theta e to the negative y over 2 theta. So it's at this point where you can start simplifying, and some of the simplification is easy. The theta on the bottom here cancels out with the theta up front. How can you manipulate the first exponential term? What do you do when you have an e to a power to a power?
You multiply the powers.
Bingo. And so I know that's often something that isn't recalled or you may be uncertain of. And so this is e to the negative y over 2. So I'm multiplying y over 2 theta by theta minus 1. So when you multiply by theta, the theta cancels out. And when you multiply by negative 1, you get plus y over 2 theta. And all of that's inside the power of the first exponential term. I have the 1/2 lingering, and I have an e to the negative y over 2 theta. So then my next question is, what do you do with the powers when they have the same base? And so you have an e to a power times an e to a power. What do you do with those powers? You add them. Good job, Miku. So when you add them, hopefully you see that this positive y over 2 theta is going to cancel out with this negative y over 2 theta, which leaves us with 1/2 e to the negative y over 2. And then you think about the support. So x goes from 0 to 1, that was given, and y equals negative 2 theta log x. And so as x goes towards 0, because the natural log function doesn't actually exist at 0, but as you go closer and closer to 0, does anyone know what the natural log function is approaching? This is your natural log curve. And so as you get closer and closer to 0, so as you're going along the x-axis this way, your natural log function is going towards negative infinity. And so here we've got negative infinity as our lower bound. And then as x goes to 1, natural log is, what's the natural log of 1? 0, good. And even though it's multiplied by negative 2 theta, it's still going to be 0. So that's our support for this scenario. Actually, I switched something. So the natural log function is going to negative infinity, but you're multiplying that by negative 2 theta. So that actually means that this should be flipped. And your support is from 0 to infinity. All right, so the function that I sketched, that's just the natural log part. I didn't actually multiply by the negative 2 theta, but you do have to consider that when you're looking at y, because y is negative 2 theta times the natural log of x. And theta is given to be positive, so it's not going to negate it back. And then this is fine. This is the answer, but it could be useful to see if it happens to come from a known distribution. So again, if you happen to have them memorized, great. If you don't, here is your handy and dandy table. What distribution does it look like? So I see one person said geometric. So geometric, I don't have one here.
Sorry, I meant exponential.
Yes, okay. Making me nervous. Yes, exponential, Miku and Tony, with what theta value? 2, yeah. All right, so let's go ahead and just at least say that. So now we know that y is exponential where theta equals 2. It's not really necessary to write theta in there because that's just the parameter notation, but I think it just makes it clearer. So exponential 2 is a nice way of finally, saying what your ultimate answer is. And that's it. So we've gone through, I think, yeah, half the topics for this. So we may finish this topic on Thursday, and then for the rest of the term, we will get into more statistical ones. Any questions in the few minutes remaining?
Wait, you know, on the top, what is, oh no, on the top of this problem, you did, v of v prime of y, and then you took the derivative.
Mm-hmm.
Wait, why do you, like, I know that the top kind of talks about that, but like, why didn't you do that for like the previous problems and stuff?
Because there's a separation on what to do depending on whether it is continuous or discrete. And so discrete actually doesn't use the v prime part, whereas continuous does.
So this is continue. Oh yeah.
Mm-hmm. That's what you're looking for, right?
Yeah.
Whoop. Anyone else with a question? Okay, you're very welcome. I did during the little break. I did post the last 2 lectures that are on YouTube. I did put a link up on Lolima if you happen to rewatch these lecture videos, and I'll try to do this one sooner. So it takes a little bit for it to download first of all, and then for YouTube to create the closed captioning. But I'll try to get that up within the day or so. Other than that, enjoy the rest of your week, and I will see you guys on Thursday.
You know how it's